Hi student, welcome to the Digital Control System Lab demo. And for the course we have prepared two demonstrations to show you guys about the basics of control theory using the simplest setup. So the setup we built is motor speed control and motor position control. So as you can see, the hardware in the little window aside of this Pinapto recording, I would like to remind you that I'm capturing two screens right now. So when I will refer to the second screen, you have to switch the screen so that you can actually see what's happening on the MATLAB part. But the one screen is dedicated to the presentation that I'm playing. So you have to switch screen back and forth when I say so. So right now we are on the screen 1, so you can see the presentation that I'm showing you, the lab demonstration, on which you can see the first is the motor speed control, second is the motor position control, and the second screen, if you see, there's a MATLAB I just opened up to play the files. And on the third part you see there's a hardware you can see that we're going to run in this video during this demo. So before going into that, moving into the presentation, so you need to make sure that you switch the screen when required. So the motor position control experiment, in this experiment we'll actually try to give a student a little bit overview of feedback control theory, which will include for this part is basically give you a basic proportional control theory and how we can implement the basic proportional control on the motor speed control setup, and also the integral control to eliminate the steady state error, because the proportional control is not able to remove the steady state error in your system. So we will see how when we will introduce the integral control, so how it eliminates the steady state error. And then we'll kind of show you the trade-off between proportional and integral control, so that you can observe when you have a proportional control in real time, how you can remove the steady state error by just kicking in the integral control to see a clear change in the transient performances of your system. In this case is the motor speed control system. So in the last part we will also give an overview of PI gain design, so with the pole assignment method. So we'll actually try to place the pole at different locations to actually make the system response better. So these are the four topics that we'll cover in this demonstration of motor speed control experiment. Before moving forward into the presentation, you see the hardware that we are actually using, the configuration for the speed control system. So the Arduino we are using, we are taking the analog inputs, obviously, because we have analog output of the sensors, the tachometer that in this setup, and also we have the digital output we are using through which we are generating the PWM waveforms to actually switch the FET amplifier to run the motor. The FET is basically responsible to drive the motor in this case. So the one motor is powered and one is we are using as a tachometer, as a sensor, and at the output you see there is a low pass filter right here. So low pass filter is actually responsible to remove the noise or to suppress the noise from the motor as much as it can to give a better reading at the A0 input of the Arduino. So here, if you look at the hardware setup, so this motor is powered and the second motor is used as a tachometer, and this is the potentiometer to actually give you the speed commands that you can see in the block diagram. And also we have the diodes to actually to block the flow, reverse current flow in the circuit, not to damage the Arduino. And then we have a FET right here, and the circuitry is pretty much simple in this case. And so these are the two motors, DC motors, that we have used in this case. So so here's the experimental setup diagram that we have This is the one that you are looking at it right now. So this is exactly the setup that we built for the motor speed controls experiment. So let's start by testing the motor operation using the MATLAB. So in this case, you will see I will actually test the general operation, a motor operation, and will try to increase the speed of the motor by using this potentiometer. And then, as you can see in the presentation part screen, that we have a yellow graph and the blue graph. So the yellow graph is basically the input that we're giving from the potentiometer, and the output we are measuring from the blue graph is basically the motor is trying to coop up or speed up as we ramp up the potentiometer voltage. So you have to go back to this switch screen to the screen 2, and then you'll see I'll be running the file for just to check the motor operation, just to show you guys the same graph that I've included. So as you can see, the motor is running, so I'm trying to increase the voltage, and I have to decrease it, and then also increase and decrease it. So it's just increasing the voltages as we increase the voltage from the potentiometer, and it will increase the voltage to the motor, and then we are measuring the speed from the tachometer. So as you can see in this graph, I'm working in screen 2 right now, so you can see this is the graph that's like the similar with the presentation that we have included. So this is just the motor testing operation here. So coming back to the presentation, we have next we will test the basic proportional control. So basic proportional control is a simple controller that we have an input target value, and then we have a deviation obviously from the output that we are measuring to the tachometer sensor, is an analog sensor, and we have a controller, proportional control, and the control object is your DC motor. So the proportional controller will keep on actually working until there is a deviation from the target value. So if there is an error, obviously the controller will keep pushing to make it 0, but the proportional control will never be able to make the steady state error 0. So that's why we need integral control for eliminating the steady state errors. So I just wrote it here as well, that the output is detected by a sensor, which is in our case is tachometer, compared to the target value that we have set in the simulation files. And depending on the deviation, the control input is obviously being generated by the proportional control, and that part determines the control input from the deviation is called controller. Obviously controller's responsibility is to generate the control input to drive your system. So moving forward, we will actually test the system on 4 gains. Just want to show you guys that at different proportional gains, your you have a different system response. So I'll try to show you the setup that we have built, the motor plus speed control response on these four set of P gains. So we'll switch to the screen 2. So this is the case for the proportional gain 2, as we selected the Kp is equal to 2. So as you can see, the motor is running at this point. So we are giving the reference signals in the yellow, and the P controller output is this blue graph. So this is the case for the gain 2, and for running the setup for the gain 4, we use the gain 4 here, and then run the setup. I'm working on screen 2 just to let you know. You have to switch the your screen to second screen so you can see. So we have run the setup now at Kp is equal to 4. So this is the second case, as you can also see in the screen 1 that the pictures that we are included. Pretty much we're getting the same results here. So we'll keep on changing to the third value of the proportional gain, which is 8, and then we'll run the setup. As you can see, this as we are kept on increasing the proportional gain, the blue graph is actually try to coping up the reference signal, which is the yellow one. So there here we have a